So today let's discuss questions of mean value theorem and Taylor expansion basically. So the question 1 says that expand ln x in power of x minus 1 using Taylor's theorem, and we are also supposed to find the value of ln 1 minus x, and we are supposed to find this value correct up to 4 decimal places. So we are supposed to expand ln x, but I can write ln x as ln 1 plus x minus 1. And if I let x minus 1 equals to y, then my expansion of ln x is same as expansion of ln 1 plus y. So we'll basically expand ln 1 plus y using Taylor's theorem, and then we'll substitute value of y therein. So the Taylor's expansion is basically fx is equals to fa plus x minus a into f dash a plus x minus a square into f double dash a divided by derivative of 2 plus derivative of n times a divided by n factorial into x minus a raised n, where x lies somewhere in neighborhood of a. So this is the Taylor's expansion. So to find Taylor's expansion around y equals, so we are supposed to find Taylor's expansion of ln x. For that we need to find out derivative, first derivative, second derivative, and the other derivatives as well. So Taylor's expansion of ln 1 plus y around y equals to 0 will be basically f of x, that is basically ln x only. So my ln x is equals to ln 1 plus y, and I am finding the Taylor's expansion around y equals to 0, so it will be basically f0 plus y minus 0 into f dash 0 plus y minus 0 square into f double dash at 0 divided by 2 factorial and fn 0 divided by n factorial into y minus 0 raised n. So my fx here is ln, fy is ln 1 plus y. So f of 0 will be basically ln 1 plus 0, that is ln 1, and ln 1 is 0. So f0 is 0. Likewise, I am supposed to find first derivative of f, that would be f dash y, that is equals to 1 plus y, and its value at 0 is basically 1. Likewise, I can find second derivative, that will be basically minus 1 of 1 plus y square, and its value at 0 will be minus 1. And if I find third derivative of f, so it will be minus 1 into minus 2 divided by 1 plus y cube, and its value at 0 will be 2. Likewise, I can find fourth derivative, that will be basically minus 1 into minus 2 into minus 3 divided by 1 plus y raised 4, and its value at y equals to 0 will be minus 2 into 3 divided by 1 when we put y equals to 0. So it will be minus 3 factorial. So if you observe that it follows a pattern, so using that pattern we can say that derivative of f n times will be basically minus 1 into n minus 1 into n minus 1 factorial divided by 1 plus y raised n, and its value at y equals to 0 will be basically minus 1 raised n minus 1 into n minus 1 factorial. Now if I substitute these values in star 1, I'll be getting ln x as ln 1 plus y, which is equals to f0, that is 0, plus y into f dash 0, that is 1, plus y square divided by 2 factorial into f double dash 0, that is minus 1, plus y cube divided by 3 factorial into f triple dash 0, that is 2. Likewise yn divided by n factorial into derivative of n times at 0, that is minus 1 raised n minus 1 into n minus 1 factorial, and so on. So my ln x is equals to ln 1 plus y, which is equals to y minus y square by 2 plus 2 into y cube by 3 factorial plus y raised n by n factorial into minus 1 raised n minus 1 n minus 1 factorial, and so on. And this term is equals to y minus y square by 2. So if I expand 3 factorial, I'll be getting 3 into 2, and the 2 in numerator balances the 2 in denominator. So I'll be getting y cube by 3 minus y4 by 4, and so on. And on nth term, I'll be getting y raised n by n, because I can write n factorial as n into n minus 1 factorial, and this balances this one. So this is basically the Taylor's expansion of ln x, which is also equals to ln 1 plus y. But in the earlier we have assumed that y is basically equals to x minus 1. So if I put in value of y, I'll be getting ln 1 plus x minus 1, which is equals to ln x, and this term is equals to x minus 1 minus x minus 1 square divided by 2 factorial plus x minus 1 cube divided by 3. We can remove this factorial thing, minus x minus 1 raised 4 by 4, and so on. Divided by n. So this is basically Taylor's expansion of ln x in terms of x minus 1. And in the question further, we are supposed to find value of ln 1.1. So ln 1.1 will be basically equals to 1.1 minus 1 minus 1.1 minus 1 square by 2 plus 1.1 minus 1 cube by 3 plus minus 1.1 minus 1 raised 4 by 4, and so on. So this thing will be basically equals to 0.1 minus 0.1 square by 2 plus 0.1 cube by 3 minus 0.14 by 4 plus 0.15 by 5, and so on. So we are supposed to find its value correct up to 4 decimal places. So for that you need to check like how many terms you need to include in the expansion to get it correct up to 4 decimal places. So if I solve using first 3 decimal, like if I approximate ln 1.1 using first 3 terms, so I'll be getting 0.1 minus 0.1 square into 0.5 plus so if I do it till third term, I'll be getting so I am getting, if I do it till third term, 0.095333, and if I do it till 4 terms, I'll be getting ln 1.1 into 0.095308. So this is approximation till third term. This is approximation till fourth term. So we are supposed to calculate a correct approximation up till 4th decimal point. So if you observe that this is correct up to 4 decimal points, so we are supposed to calculate ln 1.1 till 4 using 4 terms. So this is the correct approximation of ln 1.1. So let's move on to next question. So the next question says that show that between two roots of e raise x into cos x equals to 1, there exists at least one root of e raise x sin x minus 1. So since there is no exact root given to us, so we'll assume that there are two roots. So let a comma b be roots of e raise x cos x equals to 1. So from here I can say that a comma b are roots of cos x equals to e raise minus x, or I can write this function as cos x minus e raise minus x equals to 0. So if a and comma b are roots of this, so these will be satisfying this function. So we'll get cos a minus e raise minus a equals to 0 and cos b minus e raise minus b equals to 0. So for convenience, let's name this function as fx. So I got f of a equals to 0 and f of b equals to 0 because I have assumed that a and b are basically roots of fx. And for we can assume that a is less than b. Then if you see that this function fx, that is cos x minus e raise minus x. Cos x being trigonometric function is a continuous function. Also this e raise minus x is exponential function, is also continuous function, and we know that sum of two continuous function is a continuous function. So from here I can say that fx is a continuous on closed interval a comma b. Also you can observe that fx is basically a differentiable function in a comma b. Usually the questions asked in that the function is continuous and differentiable only, but if like just for clarification purpose you can check for yourself on the rough page, but usually it's differentiable only. You can just look for if there is any problematic point you find. So fx is differentiable in a comma b. Then using Lagrange's theorem, there will exist c in open interval a comma b such that derivative of f at c will be equals to fb minus fa divided by b minus a. But we have already seen that a and b are roots of function fx, so f of b and f of a both are 0. So from here I'll be getting my f dash c is equals to 0, where c is in between a comma b, open interval a comma b. So now let's just find out derivative of function fx, that is cos x minus e raise minus x. So if I take its derivative with respect to x, I'll be getting minus sin x plus e raise minus x. So from here I'll be getting my f dash c is equals to minus sin c plus e raise minus c is equals to 0. That is same as saying I can multiply by e raise c throughout, so I'll be getting e raise c into sin c plus 1 is equals to 0. So from here I can see that also my c is in between open interval a comma b, so I can easily say that there exists c belonging to a comma b such that 1 minus e raise c sin c is equals to 0. So c is basically acting as root of 1 minus e raised x sin x equals to 0, and c belongs to open interval a comma b. So from here I can conclude that there exists a root c of this function in between two roots of function fx, and that's what we are supposed to show in this question. So let's move on to next question. So the next question says that it asks us to check if this function fx verifies the condition of mean value theorem. So fx is given to us as x plus 1 by x, and it asks us to verify conditions in interval 1 by 2 comma 3. So if you see that fx is basically sum of two functions, that is x and 1 by x, and the only problematic point for continuity and differentiability of this function can be x equals to 0 only. But we're supposed to check the conditions of mean value theorem in interval 1 comma 2 to 3, and 0 doesn't belong to this interval, so we can safely say that fx is continuous in 1 comma 2 to 3. You can also verify this. Also we can say that fx is differentiable in open interval 1 comma 2 to 3. Now the third condition that we imply from mean value theorem is, if these two conditions are satisfied, then there must exist c belongs to open interval 1 comma 2 to 3 such that f dash of c must be equals to f of 3 minus f of 1 by 2 divided by 3 minus 1 by 2. So we supposed to see if there exists any such c in between open interval 1 comma 2 to 3. So for that, let's just calculate f dash c. So my f dash c will be basically equals to f of 3, that is 3 plus 1 by 3 minus f of 1 by 2, that is 1 by 2 plus 2 divided by 3 minus 1 by 2, that gives me 5 by 2. So from here I'll be getting f dash c as 3 minus 2, that is 1, plus 1 by 3 minus 1 by 2 divided by 5 by 2. So this thing is basically equals to 1 plus, if we take LCM we'll be getting 6, and 2 minus 3, that is minus 1 divided by 5 by 2. This is equals to 5 by 6 divided by 5 by 2, and this gives me f dash c is basically equals to 1 by 3. Now let's just take derivative of function fx at point c. So we'll be getting 1 minus 1 by c square is equals to 1 by 3. So if I solve it for c, I'll be getting 1 by c square is equals to 2 by 3. So from here my c square is 3 by 2, and if I take under root of both sides, I'll be getting under root 3 by 2 plus minus under root 3 by 2. But I have assumed that, like using the condition of mean value theorem, I have assumed that my c is in between one open interval 1 comma 2 to 3. So from here I can discard the negative c, so I can say that my c is under root 3 by 2, which is basically under root 1.5, and that lies somewhere in between 1 comma 2 to 3. So we got a point c in between open interval 1 comma 2 to 3 such that this condition that is given in question is satisfied. So let's move on to next question. So the next question says that find the Taylor expansion of the function fx equals to log 1 plus x, where x lies in between infinity to minus 1 to infinity. So from here I can say that 1 plus x will lie in between infinity to 0 to infinity basically. So we are supposed to find the Taylor expansion about x equals to 2 with Lagrange's form of remainder after 3 terms. So we have already seen this expansion of fx, that is log 1 plus x, in the first question. So we got our expansion as fx is equals to f2 plus x minus 2 into f dash 2 plus x minus 2 square into f double dash 2 divided by 2 factorial plus f dash 3 into 2 into x minus 2 cube by 3 factorial and so on plus Rn, where Rn is the Lagrange's form of remainders, and my Rn is basically fn plus 1 into 2 divided by n plus 1 factorial into x minus 2 raised n. So my expansion will be basically fx is equals to f2, that is log 1 plus 2, that is log 3 plus x minus 2 into f dash 2. So we are supposed to calculate f dash 2, f double dash 2 and so on. So first let's do that. So my function fx is log 1 plus x. So from here if I take derivative of it, I'll be getting 1 upon 1 plus x. Likewise its double derivative will be minus 1 upon 1 plus x square. Its triple derivative is minus 1 into minus 2 divided by 1 plus x cube and so on. And derivative of value of f at x equals to 2 is log 3. First derivative at x equals to 2 is 1 by 3. Likewise second derivative at x equals to 2 is minus 1 upon 3 square, and third derivative at x equals to 2 is 2 divided by 3 cube and so on. So from here my fx, that is Taylor's expansion of f around x equals to 2, will be log 3 plus x minus 2 into f dash 2. So f dash 2 is 1 by 3 plus x minus 2 square by 2 factorial into f double dash 2, that is minus 1 by 3 square plus and so on. We are supposed to find Lagrange's remainder after third term, so that will be Rnx and n is greater than 3. So where Rnx, that is Lagrange's form of remainder, is basically fn plus 1 at some point c divided by n plus 1 factorial into x minus 2 raised n plus 1. So that's the Lagrange's form of remainder for Taylor expansion of fx equals to log 1 plus x. So let's move on to next question. So in the next question it asks us to justify the Rolle's theorem or mean value theorem, that there is no number k for which the equation has two distinct solutions in interval minus 1 to plus 1. So let us assume on contrary lines that there exists k. Let there exist k such that fx, that is x cube minus 3x plus k, has two distinct roots in interval minus 1 comma 1. So let a comma b be roots of fx. Also we have assumed that there are two distinct roots, so from that we can say that a is not equals to b. So either a is greater than b or a is less than b. So without loss of generality we can assume that a is greater than b. Likewise we can prove the same result for a less than b. So without loss of generality we can assume that a is greater than b. So if you see that fx being a polynomial function is continuous in interval minus 1 comma 1, likewise fx is differentiable in open interval minus 1 comma 1, then using the mean value theorem there must exist c there must exist C in between open interval -1, 1 such that f of f of a minus f of b divided by a minus b. We are using Lagrange's theorem on open interval a comma b. Since fx is continuous in 1, 1, so from here we can say that fx is continuous in closed interval a comma b. Likewise, fx is differentiable in open interval a comma b. Then by Lagrange's theorem, there must exist C in between b comma a. We have assumed b to be smaller, so this interval must be b comma a. So, but we have assumed that a and b are basically roots of fx. So f of a and f of b must be 0. So from here I got f dash c must be equals to 0, where c belongs to a b comma a. Now my function fx is basically x cube minus 3x plus k. So if I take its derivative, I'll be getting 3x square minus 3. But by mean value theorem, I got that for some c in between b comma a, my f dash c must be equals to 0. So that is 3c square minus 3 must be equals to 0. So from here I got c square is equals to 1. That is c must be equals to plus minus 1. So I got c as plus minus 1, for which the derivative of function fx is equals to 0. But this gives us a contradiction because we have assumed that c lies between open interval b comma a. Even if I take my roots, distinct roots as 1 comma minus 1, then also my c doesn't belong to open interval 1 comma minus 1. So from here I can see that c doesn't belong to c, that is plus minus 1 doesn't belongs to open interval b comma a. So my assumption that there exists k such that fx has two distinct roots in interval -1, 1 is incorrect. So from there we can say that there does not exist any such k. That's all we are supposed to prove in this question. So let's move on to next question. So the next question says that if f is a function from closed interval a comma b to r, and it is given that it's continuous, f is continuous in closed interval a comma b, and f is differentiable in open interval a comma b. So this f is a function, continuous function on closed interval a comma b and differentiable on open interval a comma b. Also it is given that a is greater than 0 and b is greater than a. So our claim is there exists c in between a comma b such that f of b minus f of a must be equals to c into f dash c into log b by a. So if you observe that in the question it is given that f is continuous and f is differentiable, so it basically satisfies the necessary condition for using the mean value theorem. So from there we can easily use mean value theorem in this question. So first let's observe what we are supposed to prove in this question and then we'll move forward. So we are supposed to show that there exists c in open interval a comma b such that f of b minus f of a divided by, I can take this log b by a on left hand side, so I'll be getting log b by a equals to c into f dash c. That is basically, I can write it as f of b minus f of a divided by log b minus log a, and this thing is equals to f dash c divided by 1 by c. I can write it as this. So if you observe that if I take another function, let's say gx, that is log x, so if I take that, so I can easily achieve this form using Lagrange's Cauchy's mean value theorem. So what Cauchy's mean value theorem says that if fx comma gx are two continuous functions on closed interval a comma b and differentiable on open interval a comma b, then, and also derivative of g function g dash x is not equals to 0 for all x belonging to open interval a comma b, then there exists c belonging to open interval a comma b such that f of b minus f of a divided by g of b minus g of a is equals to f dash c divided by g dash c. This is basically the Cauchy's mean value theorem. So if you observe that to prove this, I can assume my function gx to be log x, then I can get this, because derivative of g will be g dash x will be basically 1 by x. So if I assume that gx is equals to log x on interval a comma b, and here in the question itself they have given that a is strictly greater than 0, so my function gx is continuous on a comma b and differentiable on open interval a comma b. Also if I take derivative of g with respect to x, I'll be getting 1 by x, and it is nowhere equal, it is not equals to 0 for any x in between a comma b. So from there I can see that my necessary conditions for applying Cauchy mean value theorem are satisfied. So if I use Cauchy's mean value theorem, I'll be getting f of b minus f of a divided by g of b minus g of a is equals to f dash c divided by g dash c. So this thing will be equals to f of b minus f of a divided by g of b is log b minus log a is equals to f dash c divided by g dash c, that is 1 by c. So if I simplify it, I'll be getting fb minus fa divided by log b by a is equals to c into f dash c. So from here I got fb minus fa is equals to c f dash c into log b by a, and where c is lying in between open interval a comma b, and that's what we are supposed to show in this question, that is there exists c in open interval a comma b such that this condition is satisfied. So usually in mean value theorem, first thing what you can do is you can see what we are supposed to prove and simplify it to see like if there is any theorem which you can directly apply on it rather than just solving it directly. So let's move on to next question. So the next question says that phi and psi are two functions derivable in a comma b. So it gives us that phi and psi are two differentiable functions in closed interval a comma b. Also it gives that phi x into derivative of psi x minus psi x into derivative of phi x is greater than 0 for any x in this interval, that is for all x belonging to closed interval a comma b. Then we are supposed to show that between two consecutive roots of phi x in a comma b, there lies exactly 1 root of xi x. Okay, so we claim that between two consecutive roots of phi x equals to 0 in closed interval a comma b, there exists 1 root of xi x. So now if you see that it is given to us that phi and psi are two differentiable functions. So if phi and psi are two differentiable functions, so from here I can say that phi and psi are continuous as well in interval a comma b, because differentiability is a sufficient condition to claim a continuity of any function. Now let us assume that let alpha comma beta be two consecutive roots of phi x equals to 0 in interval a comma b, and since alpha beta are two consecutive roots of phi x, so from here we can say that there is no root of phi x in between alpha comma beta, that is there does not exist any gamma in between alpha comma beta such that phi of gamma is equals to 0. Now since alpha beta are root of phi x, so phi of alpha is equals to phi of beta is equals to 0. Also, so we are supposed to prove that if that's the case, so there exists exactly one root of phi x in between two consecutive roots of phi x. So on contrary, let us assume that there does not exist any root of psi x in between alpha comma beta. That means psi x is not equals to 0 for all x in between alpha comma beta, because there is no root of psi x in between alpha comma beta. Now if that's the case, I can assume a function capital F dash x as phi x upon psi x, and this function is defined because phi x and psi x are both continuous function. So I am assuming this function on alpha comma beta. So this function is basically division of two continuous function. So this function capital Fx is continuous and capital Fx is also differentiable on interval alpha comma beta. Now if you see that f of alpha will be basically phi of alpha divided by psi of alpha, and my phi of alpha is 0, so f alpha is 0. Likewise f beta is phi of beta divided by psi of beta, and my phi beta is again 0, so f beta is also 0. So if you see that this satisfies condition of Rowley's theorem, so we will get there must exist any c in between alpha comma beta such that f dash c is equals to 0. So if we find f dash c, so we'll be getting phi c into phi dash c minus phi c into xi dash c divided by xi c square. This thing must be equals to 0. So from here I got phi c into phi dash c minus phi c into xi dash c is equals to 0, where c is lying in between open interval alpha comma beta. But in question itself they have given us that phi x into psi dash x minus xi x into phi dash x is strictly greater than 0 for all x in interval a comma b. but we got that it is equals to 0, so we got a contradiction. So from here we can say that our assumption that is there is no root of xi x in alpha comma beta is incorrect. If that is incorrect, so from there we can say that there exists at least one root of xi x in between alpha comma beta. So this is the one thing that we are supposed to prove in question, that is there exists one root of xi x in between two consecutive roots of phi x. But if you see that in the question it says that there exists exactly one root, but right now we have proved that there is at least one root, so we have not shown that that root will be the only root of xi x in between alpha comma beta. So let's prove that there exists exactly one root of xi x in between alpha comma beta. Now let us assume that r comma s are two roots of xi x in alpha comma beta. So that will, and let us say that r is not equals to s and r is less than s, so we'll be getting alpha less than r, less than s, less than beta. Now if I perform the similar operations on a function, let's say capital Gx equals to xi x divided by phi x. So using the similar logic that we have done for capital Fx function, I'll be getting that there exists one root of phi x in between r comma s. So from here I can say that there exists one root, at least one root of phi x in between alpha comma beta, because if phi x has root in between r comma s, then phi x has root in between alpha comma beta also, because r comma s is contained in alpha comma beta. But if you see that we have assumed earlier that alpha comma beta are consecutive roots of phi x, that is there is no root of phi x in between alpha comma beta, so we got a contradiction to our assumption. So from this we can say that there is exactly one root of phi x of psi x, sorry, in between alpha comma beta, that is the two roots of phi x. So this is what we are supposed to prove in this question. So let's move on to next question. So the next question says that using mean value theorem, show that the function fx is constant in closed interval a comma b if f dash x is equals to 0. So in the first part of question we are supposed to show that fx is constant if f dash x is equals to 0 in a comma b. Let us assume that x1 comma x2 belongs to open interval a comma b and x1 is less than x2. Also let's assume the necessary conditions for applying mean value theorem, that is let our function fx is continuous in closed interval a comma b and differentiable in open interval a comma b. Then from here I can say that it is continuous in closed interval x1 comma x2 and differentiable in open interval x1 comma x2. Then it satisfies the necessary conditions for mean value theorem. Then by using mean value theorem, there must exist c in between open interval x1 comma x2 such that derivative of f at c must be equals to fx2 minus fx1 divided by x2 minus x1. But in the question it is given that derivative of fx at any point in closed interval a comma b is 0. So from there we can see that derivative of f at c will be 0 because c is point in x1 comma x2 and that is contained in closed interval a comma b. So from here I got f of x2 minus f of x1 divided by x2 minus x1 is equals to 0. So from here I got f of x2 is equals to f of x1. But I have assumed that x1 and x2 are any arbitrary point in open interval in closed interval a comma b. So we can say that f of x is equals to f of y for all x comma y in between a comma b. So from this we can conclude that fx is a constant function in a comma b. So this is the first part of the question, and in second part of the question we are supposed to show that fx is decreasing function in open interval a comma b if f dash x exists and is less than 0 everywhere in a comma b. So we claim that fx is decreasing. Fx is decreasing in open interval a comma b if f dash x is less than 0 for all x belonging to open interval a comma b. So we can assume all the necessary conditions for function fx like we did in previous question, that is all these conditions, that is it is differentiable and continuous on x1 comma x2. Then if we use a mean value theorem, then there must exist c in between x1 comma x2 such that f dash c must be equals to fx2 minus fx1 divided by x2 minus x1. But in the question it is given that, and this thing is contained in a comma b, but in the question it is given that f dash x is less than 0 for all x belonging to a comma b. So from here we can see that f dash c will less than equals to for some c in open interval a comma b. So from here I got f of x2 minus f of x1 divided by x2 minus x1 will be less than 0 for some c in open interval a comma b. So from here I can say that f of x2 minus f of x1 is less than 0, that is f of x2 is less than f of x1. But if you see that we have assumed earlier that my x1 is less than x2, so I got f of x2 is less than f of x1 when my x1 is less than x2. But x1 comma x2 I assumed as any arbitrary points in the interval a comma b. So from here I can say that f of x is less than f of y for any x greater than y and x comma y are in open interval a comma b, and this is basically the definition of decreasing function in any interval a comma b. So from here we can see that f is basically a decreasing function. So let's move on to next question. So in this question we are supposed to prove this relation where x is greater than 0. So to prove this relation it's enough to show that x plus 1 by x is less than log 1 plus x, and likewise the second relation, that is log 1 plus x less than x. So what we'll do is we'll separately show these two relations and then we'll club in together to show this relation. So for the first relation, let us assume that fx is any function equals to log 1 plus x minus x by 1 plus x. So if somehow I can show that fx is greater than 0 for x greater than 0, then I can conclude this part. So let us take derivative of this. So that will be 1 upon 1 plus x minus 1 plus x into 1 minus x into 1 divided by 1 plus x square. So f dash x is basically equals to 1 divided by 1 plus x minus 1 divided by 1 plus x square, and this term is basically equals to 1 plus x minus 1 divided by 1 plus x square. So my f dash x is basically equals to x divided by 1 plus x square, but in the question it is given that x is greater than 0. So if x is greater than 0 and 1 plus x whole square is always greater than 0 for x greater than 0, so from here I can say that f dash x is greater than 0 for all x greater than 0. So this shows that my function fx is increasing function. So if it is increasing function, so my fx is greater than f0 for x greater than 0. So from here I got my fx greater than f0. So f0 is basically log 1 minus 0, and log 1 is 0, so f0 is 0. So from here I got my fx is greater than 0, that is log 1 plus x minus x divided by 1 plus x is greater than 0, which is same as saying log 1 plus x is greater than x by 1 plus x. So I got this relation, let's name it as 1. Likewise for second part, let us assume another function gx, that is x minus log 1 plus x. Like we did in for the first relation, we'll show that gx is basically increasing function for x greater than 0 and derive this relation. So let's take derivative of g, that is 1 minus 1 divided by 1 plus x. This is equals to 1 plus x minus 1 divided by 1 plus x. So my g dash is equals to x divided by 1 plus x, and for x greater than 0, 1 plus x is greater than 1. So from here I can say that g dash x is basically greater than 0. So from this I can conclude that gx is basically increasing function for x greater than 0. So since my x is greater than 0, so my gx must be greater than g0, because we have proved that gx is an increasing function. So my gx, that is x minus log 1 plus x, must be greater than g0, that is 0 minus log 1, that is again 0. So from here I got x is greater than log 1 plus x. So using 1 and 2, I can say that x divided by 1 plus x is less than log 1 plus x, and this thing is less than x. So this proves the relation for x greater than 0. So this is what we are supposed to prove in this question. Usually for these types of question wherein we are supposed to prove the inequality between 2-3 functions, usually showing them increasing or decreasing works. So you can try this method for these type of questions. So let's move on to next question. So in the next question we are supposed to use mean value theorem and find a point on curve C defined on 2, 3 where the tangent is parallel to the chord joining the endpoints of the curve. So we are given a function y which is equals to under root x minus 2, and y is defined on 2, 3. So we are supposed to find point in between 2, 3 such that the tangent at that point is parallel to chord joining the endpoints of curve. That is, we are supposed to find point in 2, 3 where the chord joining point 2 to 3, that is chord joining 2, let's write it as f of x, f2 to 3, f3 is parallel to tangent at this curve. So if you see that this is basically the geometric meaning of geometric interpretation of mean value theorem, that is the point C which we get using mean value theorem, is a point at which tangent is parallel to the chord. So if you see that function fx, that is equals to y equals to under root x minus 2, is continuous in closed interval 2 comma 3. Also it's differentiable in open interval 2 comma 3. So the necessary conditions of mean value theorem are satisfied, so there must exist C in between open interval 2 comma 3 such that my f dash C must be equals to f3 minus f2 divided by 3 minus 2. So from here I got my f dash C must be equals to f3, that is under root 3 minus 2 minus f2, that is 2 minus 2 divided by 1. So from here I got my f dash x, that is 1 by 2 under root C minus 2 must be equals to 1, that is 2 under root C minus 2 is equals to 1. So if I take square of both sides, I'll be getting 4 into C minus 2 equals to 1. So from here my C will be 2 plus 1 by 4, that is C is basically 2 plus 0.25, that is my C is 2.25, and it clearly lies in between open interval 2 comma 3. So at point C, that is 2.25, tangent to the given curve is basically parallel to the chord joining points 2 and 3. So let's move on to next question. So the next question is prove that they're between. So this is a repeated question, we have done this question earlier, you can refer that. So let's move on to next question. Find C of mean value theorem if fx is this. Fx is basically x into x minus 1, x minus 2, my a is 0, b is 1 by 2, and C we are supposed to find. So if you observe that the function fx being a polynomial function is continuous, that is fx is continuous in open closed interval 0 comma 1 by 2, because a is 0 and b is 1 by 2, and fx is differentiable in open interval 0 comma 1 by 2. Then by mean value theorem, there must exist C in between open interval 0 comma 1 by 2 such that f dash C must be equals to f1 by 2 minus f0 divided by 1 by 2 minus 0. So from here I got f dash C must be equals to f of 1 by 2, that is 1 by 2 into 1 by 2 minus 1, 1 by 2 minus 2 minus f of 0, that will be 0, divided by 1 by 2. This 1 by 2 balances this one. So my f dash C must be equals to minus 1 by 2 minus 3 by 2, that is equals to 3 by 4. So if I take derivative of function fx at x equals to C, so that will be C minus 1 into C minus 2 plus C into C minus 1 plus C into C minus 2, and this thing must be equals to 3 by 4. So if I simplify it, I'll be getting C square minus 3C plus 2 plus C into C 2C minus 3 is equals to 3 by 4. So on simplifying, I'll be getting C square minus 3C plus 2 plus 2C square minus 3C equals to 3 by 4. So this thing is equals to 3C square minus 6C plus 2 minus 3 by 4 equals to 0. So from here I got 3C square minus 6C plus 5 by 4 equals to 0. That is equals to 12C square minus 24C plus 5 equals to 0. And if you see that this is basically a quadratic equation in terms of C, so we can easily solve C. So C will be basically equals to 24 plus minus under root minus 24 square minus 4 into 12 into C, that is 5, divided by 2 into 12. So my C is basically 24 plus minus under root 24 into 14 I'll get. So this will be basically equals to 24 into 24 minus 4 into 12 into 5. 336 divided by 24. So I can write 336. You can easily simplify it and get value of C. So we'll be getting two value of C, and you can see if both or only one value of C lies, it being interval 0 to 1/2. So let's move on to next question. So the next question says that if A0, A1, A2 and An are real numbers, that is A0, A1, A2 and so on, An are real numbers, and it is given that A0 by n plus 1 plus A1 by n plus A2 by n minus 1 and so on plus An minus 1 by 2 plus An is equals to 0. Then we are supposed to show that there exists at least one real number x in between 0, 1 such that this is equals to 0. So there is nothing given to us about function fx, but if you see that this, we are supposed to prove that A0 xn plus A1 x raised n minus 1 plus A2 x raised n minus 2 plus A raised n minus 1 x plus An is equals to 0. So we are supposed to show that. So if we take integration of this, we'll be getting A0 into x raised n plus 1. This is just rough work, like the mind work. You can do it on a rough space to see what your function fx can be. So this will be basically, if I take integration of it, I'll be getting A1 into x raised n by n plus A2 into x raised n minus 2 by n minus 1 by n minus 1 and so on. An minus 1 into x square by 2 plus An into this thing x is equals to C, maybe the integration constant. So you can assume your function fx to be somewhat like A0 into x raised n plus 1 by n plus 1 plus A1 into x raised n by n plus A2 into x raised n minus 1 by n minus 1 plus Anx plus C, where C is the integration constant. So we are supposed to show that this is equals to 0 for some x in between 0, 1. So if I choose my A to be 0 and my B to be 1, then I can use a mean value theorem in between interval a, b. So this function fx that I have assumed is a polynomial function, so it is basically a continuous. Fx is continuous in closed interval a, b and differentiable in open interval a, b. So necessary condition of mean value theorems are satisfied. So if I use mean value theorem, so there must exist some, let's say, xi in between a, b such that f dash of xi must be equals to f b minus fa divided by b minus a. But I have assumed my b to be 1 and a to be 0, so from here I got my f dash psi is equals to f1. So if I see, f1 will be basically a0 by n plus 1 plus a1 by n plus an plus c minus my f0 will be, these all terms will be 0, so we'll be left with c only, divided by c divided by 1 minus 0. So this thing is equals to a0 by n plus 1 plus a1 by n plus an, this c balances this one, divided by 1. But in the question this term is given to us as equals to 0, that is a0 by n plus 1 plus a1 by n up to an is equals to 0. So from here I got f dash xi is equals to 0 for some xi belonging to a comma b. So if I take derivative of function fx, I'll be getting a naught into xi raise n plus a1 into xi raise n minus 1 plus an minus 1 into xi plus an is equals to 0, where xi is in between open interval a comma b. So this proves our result, that is there exists some x in between 0 comma 1 such that a naught x raise n plus a1 x raise n minus 1 and so on is equals to 0. So let's move on to next question. So in this question it is given that f is a function from R to, let's say, R, because nothing is given to us about range, and f of 0 is minus 3. Also f dash x is less than equals to 5 for all x in real. So we are supposed to find like what can be the largest possible values of f2. So since f dash x is less than equals to 5 for all x in real number, we can observe that the derivative of function fx is less than equals to 5. That is a constant term. So from here we can say that my function fx, let us assume that it is ax plus b, that is let it be a linear polynomial. There can all other functions fx as well that satisfies this given condition, but for the question we can say that let that function fx be a linear polynomial, because if we take derivative of it we'll be getting fx less than equals to 5x plus c, and this is a linear polynomial in x. So let us assume that our fx to be ax plus b, where a comma b are again in real. So in the question it is given that f of 0 is equals to minus 3. So from here I got minus 3 is equals to b. So my function fx is basically ax minus 3, and the question says that derivative of fx, that is f dash x, that is equals to a, is always less than equals to 5. So from here I got my a less than equals to 5 always, and we are supposed to find the large values of f that are possible. So my values of f at 2 will be basically 2a minus 3, but my a is always less than equals to 5. So from here 2a will be less than 10, and 2a minus 3, that is f2, will be less than equals to 10 minus 3, that is 7. So upper bound of f2 is 7, that is f2 can attain max value 7. Likewise from here also you can see this, because if you take f0 then that will be c, that is minus 3 less than equals to c, and then you can substitute this value of c to find a relation, and then you can find out upper bound for f2. So let's move on to next question. So the next question says that a twice differentiable function fx is f is twice differentiable, and we know that the differentiability is basically sufficient condition from continuity. So from here I can say that f and f dash are continuous and differentiable. So f is a function that is twice differentiable such that f of a is equals to 0 and it is equals to f of b, and it further says that f of c is greater than 0 for some c belonging to open interval a comma b. So we are supposed to prove that there is at least one such point xi in between a comma b for which f dash xi is less than 0. Okay. So in the question it is given that so since f is twice differentiable, so f and f dash are also continuous on closed interval a comma b and differentiable on open interval a comma b. Also there is a c in between a comma b such that f of c is greater than 0. So let's use a mean value theorem on open interval a comma c and c comma b. Since f and f dash are continuous on a comma b and a comma c and c comma b are basically subsets of a comma b only, so the continuity and differentiability, basically the necessary conditions for using mean value theorem, are satisfied for this interval and this interval as well. So I'll be getting a xi1 in between open interval a comma c such that f dash xi1 is equals to fc minus fa divided by c minus a, and there exists xi2 in between open interval b comma c such that f dash xi2 is equals to fc minus fb divided by c minus b. But if you see that fa is equals to 0, so this term will be 0, and since c is greater than a, so and fc is also greater than 0, so f dash xi is greater than 0. Likewise here it will be c to b because my c is less than b, so here it will be fb minus fc, b minus c. So my fb is 0, so it is minus fc divided by b minus c. B minus c is a positive term, and since fc is greater than 0, so minus of fc will be less than 0. So from here I got my f dash xi2 dash, that is minus fc divided by b minus c, is less than 0. So basically from here I can conclude that there exists xi1 comma xi2 such that a is less than xi1, less than c, less than xi2, and this thing is less than b. So this is a relation in between xi1 and xi2. Now since we have seen earlier that f dash is also continuous and differentiable on interval a comma b, so I can use a mean value theorem on interval xi1 comma xi2 and function f dash x. So if I use mean value theorem, then there must exist some xi belonging to open interval xi1 comma xi2 such that f double dash of xi must be equals to f dash of xi2 minus f dash of xi1 divided by xi2 minus xi1. So you can see that xi2 minus xi1 is a positive term, so we are supposed to check the sign of this to conclude that f double dash xi is less than 0. So if you see that f dash xi2 is basically equals to minus fc divided by b minus c minus f dash of xi1, that is fc divided by c minus a divided by xi2 minus xi1. So from here I can take out minus fc common, so it will be minus fc divided by xi2 minus xi1 into 1 upon b minus c plus 1 upon c minus a. This thing is equals to minus fc divided by xi2 minus xi1 into c minus a plus b minus c. This minus c balances out this, and in denominator we have b minus c into c minus a, and this thing is equal to b minus a into minus fc divided by xi2 minus xi1 into b minus c into c minus a. So using this you can see that xi2 minus xi1 is greater than 0 because xi1 is less than xi2. Likewise b minus c is also greater than 0 and c minus a is also greater than 0, that is the term in denominator is greater than 0, and b minus a is also greater than 0, and in question it is given that f of c is greater than 0. So this whole term will be less than 0 because of this negative sign. So we have proved that there exists xi belonging to a comma b such that f double dash of xi is less than 0. So let's move on to next question. So this is a repeated question. This is asked, I guess, thrice in CSE and IFoS combined. So let's move on to next question. So the next question says that suppose that f double dash is continuous on close interval 1 comma 2, that is f double dash x is continuous on 1 comma 2. So existence of this f double dash x implies that fx and f dash x are continuous and differentiable on close interval 1 comma 2 and open interval 1 comma 2 respectively. That is continuous on this and differentiable on this. And the question further says that f has 3 zeros in the interval 1 comma 2. fx has 3 zeros in interval open interval 1 comma 2, and we are supposed to show that f double dash has at least 1 zero in interval. That is, we claim that there exists some xi belong to open interval 1 comma 2 such that f double dash of xi is equals to 0. So let us assume that let a comma b comma c such that a is less than b is less than c are 3 zeros of f in open interval 1 comma 2. So from here I can say that f of a is equals to f of b is equals to f of c. And since we have seen that function fx is continuous on close interval 1 comma 2 and differentiable on 1 comma 2, so it's continuous and differentiable on a comma b as well as b comma c. So I can use mean value theorem on fx in interval a comma b. So I'll be getting a xi1 in open interval a comma b such that f dash of xi1 will be equals to fb minus fa divided by b minus a. So from here I got there is a xi1 in a comma b such that derivative of function fx at xi1 is equals to 0. Likewise, if I use mean value theorem on fx in open interval b comma c, so I'll be getting a xi2 belonging to open interval b comma c such that f dash of xi2 will be equals to 0 because f of b and f of c both are 0. So using Rolle's theorem I'll be getting f dash of xi2 is equals to 0. Now I got my a is less than xi1 is less than b less than xi2 less than c, and my a and b are basically a is greater than 1 and b is greater than less than 2 because the roots are in interval open interval 1 comma 2. So I got this relation, and I got f dash of xi1 is equals to 0 and f dash of xi2 is equals to 0. Now if I consider this interval, and we have seen that the function f dash x is continuous on close interval 1 comma 2, so f dash x is also continuous on close interval xi1 comma xi2 and differentiable on open interval xi1 comma xi2. So I can use Rolle's theorem here. So using Rolle's theorem I'll get a xi in between open interval xi1 comma xi2 such that f double dash of xi will be basically equals to 0. And that's what I guess we are supposed to prove. Yeah, so since I got a xi where So I basically got f double dash of xi is equals to 0, where xi is somewhere in between open interval xi1 comma xi2. But open interval xi1 comma xi2 is basically subset of open interval 1 comma 2. So I got f double dash of xi equals to 0, where xi is in open interval 1 comma 2. So xi is basically root of f double dash x in open interval 1 comma 2, and that's what we are supposed to prove in this question. That is, we are supposed to show that the f double dash has at least 1 0 in interval 1 comma 2, and we got that 1 0 as xi in 1 comma 2. So that's all for that question. So let's move on to next question. So the next question says that the function fh is given to me as f0 plus h into f dash 0 plus h square by 2 factorial into f double dash theta h. We are supposed to find the value of theta when h is equals to 1 and fx is given to me as this. So if h is 1, so it will be f of 1 equals to f of 0 plus f dash 0 plus 1 by 2 into f double dash theta. So we are supposed to now find value of function f dash and f double dash. So my fx is given to me as 1 minus x raised 5 by 2. So from here my f of 0 will be basically 1, f dash x will be 5 by 2 into 1 minus x raised 3 by 2. So from here my f dash 0 will be basically 5 by 2, and my f double dash x will be basically 5 by 2 into 3 by 2 into 1 minus x raised 1 by 2. So my f double dash of theta will be 15 by 4 into 1 minus theta raised 1 by 2. So let's just substitute these values in the given relation 1. So I'll be getting, also I need to find f of 1. So my f of 1 will be 0 only. So I got 1 as 0 equals to f of 0, that is 1, plus f dash 0, that is 5 by 2, plus 1 by 2 into f double dash theta, that is 15 by 4 into 1 minus theta raised 1 by 2. So from here I got it will be minus also, because using chain rule I'll be getting minus 1 as well. So I'll be getting minus 5 by 2. So from here I got 5 by 2 minus 1 equals to 15 by 8 into 1 minus theta raised 1 by 2. This is equals to 3 by 2 is equals to 15 by 8 into 1 minus theta raised 1 by 2. So if I simplify it, I'll be getting 1 minus theta raised 1 by 2 is equals to 4 by 5 basically. So I can take square of both sides. So that gives me 1 minus theta equals to 16 by 25. So from here I got theta as 1 minus 16 by 25, that is 9 by 25. So my theta is basically 9 by 25. Also 9 by 25 lies in between 0 and 1, which belongs to open interval 0 comma 1. In the next question we are supposed to prove this relation that says tan of x by x is greater than x by sin x for x in between open interval 0 comma pi by 2. So to prove this, let me assume a function fx, that is tan x by x minus x by sin x. So if I simplify it, I'll be getting tan x sin x minus x square divided by x sin x. So we know that in between open interval 0 comma pi by 2 sin x is greater than 0. Since 0 is not included in the interval, so sin x is strictly greater than 0. So now if somehow I can show that, that is the numerator part, let's name it as gx as tan x into sin x minus x square is greater than 0, then I am done with showing this. So let's just work on the function gx. So if I take derivative of gx, I'll be getting tan x is sec square x into sin x plus tan x into cos x minus 2x. So that is basically sec square x into sin x plus sin x minus 2. Now if I take double derivative of gx, that is g dash x, so that will be equals to 2 sec x, and derivative of sec x is sec x tan x, so it will be 2 sec square x tan x into sin x plus sec square x into cos x plus cos x. So this thing will be basically equals to 2 sec square x tan x sin x plus cos x plus sec x. I can subtract and add 2, so I'll be getting 2 sec square x into tan x sin x plus this term I can write it as under root cos x minus under root sec x whole square plus 2. So we know that in open interval 0, pi by 2 this thing will be greater than 0. This is also greater than 0, and because of square thing sec square x greater than 0, tan x and sin x are also greater than 0 in open interval 0, 2. So from here I can say that g double dash x is greater than 0 for x belonging to open interval 0, pi by 2. So using this relation I can say that my function g dash x is increasing function in open interval 0, pi by 2. So my g dash x must be greater than g dash 0 because my x is greater than 0. And if I calculate my g dash 0 from here, so my g dash 0 will be basically g dash 0 will be sec 0 1 into sin 0 0 plus 0, it is minus 2x. This will also be 0, so this is 0. So if it is minus 2x, so here I will get 2, so there is no need of this 2. So I got my g dash x as greater than g dash 0, that is 0 for all x greater than 0. So using this I can conclude that my gx function is increasing function for all x greater than 0 and less than pi by 2. So if gx is increasing function, so g of x must be greater than g of 0, and my g of 0 is basically from here g of 0 is 0. So my g of x is greater than 0. So using this I can say that my f of x is greater than 0 for all x in open interval 0, pi by 2. So using this I can conclude that tan x by x is greater than x by sin x for all x belonging to open interval 0, pi by 2. This proves the question, and again this is also a repeated question, so that only these many questions are asked related to this topic. So thank you for watching.